Hello students, this is the introduction to our new physics unit on torque and rotational motion. This is a physics topic which will be a relief for some of you who are less interested in the heavy biology that we've been doing so far this semester. This unit is somewhat of an extension from all of the physics that you had been doing in Integrated Science 1. In Integrated Science 1 last year, you studied Newton's laws of motion. And all of those laws and the problems that you calculated that were related to those laws all applied to objects that were traveling in a straight line. Nothing was rotating. That's the new piece this year. What I'd like you to do first is to think back to last year. If you could try to remember at least two things from your study of physics last year and call them to mind now. If you have a notebook or a blank sheet on your Notability and you're following along taking notes, just jot it down for a moment. I imagine some of the things that come to mind include Newton's three laws, and if you can rattle them off, great. The first law is, of course, called the law of inertia. An object in motion will stay in motion, or an object at rest will stay at rest unless acted upon by an outside force. The second law of motion deals with the inverse relationship between an object's acceleration and its mass for a given force. And there's a particular equation that was helpful in quantifying that. And then Newton's third law, if you remember that one, is that every force has an equal and opposite reaction force. In any case, last year what you were studying were several kinds of linear motion. In linear motion, objects either accelerate or decelerate, slow down, by an outside force acting. And with Newton's second law, an object's force is equal to its mass in kilograms times acceleration in meters per second squared. The unit for force was a Newton, which is actually equal to the mass unit kilograms, standard SI unit for mass, times the standard acceleration unit, meter per second squared. But that new quantity, Newton, may have been something that you learned for the first time last year. This year, we're studying rotational motion. And we can see a lot of similarities. First of all, the basic quantity that gets something rotating is not a force, but a torque. You may have heard that word before in truck commercials. Sometimes car companies will advertise how much torque their engines can generate and deliver to the wheels of their trucks. And that is the idea, basically, of rotational motion. The major equation governing our problems that we'll see in this unit is a very simple one, and it's very similar in format to F equals ma. It's torque equals force applied to a rotating object times something called a lever arm. The lever arm is the distance between a rotating object's pivot point, because every rotating object is rotating about some point, so wherever that point is, and where the force is applied. And if this equation is somewhat like F equals ma, the bigger the lever arm, the bigger the torque for a given force. Just as with F equals ma, the bigger the acceleration, the bigger the force that's required to get an object accelerating for a given mass. The units for torque are nothing new and nothing special. Force unit is the Newton, just like last year you learned the Newton. Lever arm length is measured in meters, and the torque unit is simply a Newton meter. Newton, sometimes Newton times meter or Newton dash meter. For all of the objects or problems that we are going to consider this year, we will consider objects that are in equilibrium. You may have heard that word before as well. Objects in equilibrium, at least from a physics standpoint, are those for which you can say the net force acting on them equals 0, which means they are not accelerating. And also, the net torque on the object is equal to 0. So that means that the object would not be rotating. So it's neither accelerating nor is it rotating. Since we draw pictures in 2 dimensions, all of the problems we encounter in this class will have this basic truth to them that the objects will be held in equilibrium. And so the torque on the left side of the pivot point will be equal to the torque on the right side of the pivot point. That's a really important equation for us to be able to use throughout this unit. Let's try one simple, straightforward. Here's a picture of a boy and a girl sitting on a teeter-totter. And while at a playground you might not want to use a teeter-totter the way this boy and girl are using it, they're sitting perfectly level, it's helpful for us in this class. I imagine when you're using teeter-totters at the playground you want to be going up and down, but for the sake of this problem we're going to say that teeter-totter is remaining motionless. It's hanging completely horizontal. And if that's true, then it's in equilibrium. And if it's in equilibrium, then we can say that the left side torque is equal to the right side torque. So the net torque is 0. And also, a side consideration is that the net force is 0 as well. Since torque consists of force times lever arm length, we can say that the force times lever arm length on the left side will be equal to the product of force and lever arm length on the right side. Let's see if that checks out in this problem. In the diagram, they're indicating the weight in newtons, that's a force, for the girl. And they're also indicating the distance that she's sitting from the pivot point, 3 meters. So 250 newtons, the force, times a lever arm length of 3 meters. On the right side, they're telling us the force due to gravity, or weight, of the boy is 500 newtons. And they're indicating a lever arm length of 1.5 meters. So the boy is sitting 1.5 meters from the pivot point, and the girl sitting twice as far away at 3 meters. Does that check out? So 250 times 3 is 750 Newton meters, and 500 times 1.5 is also 750 Newton meters. The torque on the left side is equal to the torque on the right side. This equation checks out. What I'd like you to do next, to a really good physics website called gigaphysics.com. It's one of the best ones out there. Go to gigaphysics.com. Please click on the tutorials button at the top of the screen, and you'll see 2 tutorials on our topic, torque and rotational motion. Go ahead and work through those tutorials. I imagine they will generate some good questions from you, and we will tackle those once you come to class tomorrow. Thanks for your good work.